Hello everyone. Today we will be exploring a new branch of algorithms that apply to graphs. In this lecture particularly, we will be looking at some basic concepts like graph representation and then study two graph search algorithms, namely breadth first search and depth first search. Then we will look at two applications of depth first search, which are topologically sorting a directed acyclic graph and finding strongly connected components in directed graphs. More details can be found in chapter 22 of your reference book. Before we begin, let us quickly revise what was covered in the preceding lecture, which was on disjoint sets. We learned that disjoint sets are dynamic in nature and thus support some operations. The main operations were the make set, union, and find set operations. We also saw that disjoint sets can be used to find connected components in graphs, a topic that we will be covering in more details towards the end of today's lecture. Two representations were introduced for disjoint sets. The first was linked lists, where each set was represented as a linked list with a set object and possibly multiple element objects. The second representation was disjoint set forests, where each set was a rooted tree. To reduce the running time of find set operation in forests, two heuristics were suggested, namely union by rank and path compression. Both these heuristics reduce the find path length to be proportional to the height of the tree with n elements. Now, let's enter the amazing world of graphs. I claim it to be amazing because almost everything you see around you or deal with on a daily basis is directly or indirectly networked. Look at your circle of friends, or the transportation system, or airways, or river channels. They all can be represented as networks or more generally graphs. So the idea of graph theory was first coined in the 18th century by the famous mathematician Leonhard Euler. The concept originated from a very basic practical problem. In a city called Königsberg, now located in Russia, there were 4 patches of land and 7 bridges connecting them as shown in this figure. The people of the city at that time wanted to know whether they could visit all the 4 patches of land by crossing every bridge one time only. The problem was so intriguing that it resulted in a paper being published by Euler, who formulates the problem and provides solution for various scenarios in it. For more details on this problem, I encourage you to click on this link over here and look at the video which explains it in more details. So basically, this problem can be transformed or mapped into a graph where each patch of land, let's mark them 1, 2, 3, and 4, are denoted by the nodes, and the bridges connecting these land are the edges. So basically, we have the 4 land pieces and the 7 bridges. There is a very important and widely used theorem when it comes to dealing with graphs, and that is the handshaking theorem. In the case of undirected graphs, that is graphs where edges have no specific direction, the degree of a node, say V, is defined as the number of edges connecting V to the other nodes. So for example, this arbitrary node has 3 edges, 1, 2, 3. Therefore, the theorem states that if there is some undirected graph G with V number of vertices or nodes and N number of edges or links, then the sum of the degrees of all nodes in G is equal to twice the number of edges. This is quite obvious because we count each edge twice when calculating the degree. In the case of directed graphs, however, this is not true. As we see in this figure, directed graphs have edges with directions. So you can go from one node to another only in a particular direction, and not both ways. So the degree of each node needs to be redefined as in degree and out degree. In degree is the number of edges entering a node. So for this node, the in degree is 1, since there's only one edge entering this node. Likewise, out degree is the number of edges leaving a node. So here, the out degree is 2, there are 2 edges leaving the node. Therefore, summing over all nodes in the directed graph, we would have the summation of in degrees is equal to the summation of all out degrees, which in turn is equal to the number of edges, which is n. Given a graph GVE, where V and E denote the set of vertices and the set of edges respectively, there are two commonly used representations: collection of adjacency lists and adjacency matrix. These representations can be used to characterize both directed and undirected graphs. However, depending on how connected the graph is, one representation is preferred over the other. If the graph G is sparse, that is when the number of edges is much lesser than the square of the number of vertices, then the adjacency list representation is preferred. However, on the other hand, if the graph is dense, that is E is almost equal to the square of V, then the choice is adjacency matrix. Food for thought. What would be the maximum number of edges in a graph of n nodes if the graph is undirected and if that graph is directed? Let's see how graphs can be represented using lists and matrices using this example. In the undirected graph shown here, there are 5 vertices and 7 edges. Using a linked list, it can be represented as shown over here. Here, each index holds a list of vertices to which it is connected. So over here, vertex 1 is connected to vertices 2 and 5. Vertex 2 is connected to vertices 1, 5, 3, and 4. Also, the total length of all the lists in the adjacency list representation shown here is 14, which is twice the size of the set E. In the adjacency matrix representation of this graph shown here, we have a square matrix with dimensions equal to the number of vertices in the graph. So since there are 5 vertices, the matrix is 5 by 5. The diagonal elements are all 0 because there are no self-edges, that is, edges connecting a node to itself. In undirected graphs, the adjacency matrix is symmetric. That is, for any 2 vertices that you choose, the entry for UV will always be equal to the entry for VU along the diagonal. For directed graphs, the adjacency list representation would contain vertices connected in a particular direction. Over here, since vertex 1 is connected to 2 and 4, it would be included in this list as shown here. So the sum of the length of all lists is equal to the number of edges in the graph. That is equal to E. So we can only go from node 1 to node 2 and 4 and not vice versa. Similar to undirected graphs, the adjacency matrix for directed graphs would be a square matrix, but not necessarily symmetric due to the direction of the edges. Comparing the two representations, we see that searching whether 2 vertices are connected or not in the adjacency list connection representation would take time equivalent to searching any of the lists. So if a vertex is connected to all the other vertices in the graph, the running time would be linear. To overcome this issue, the adjacency matrix allows us to search by direct indexing, which is O1 time. The downside of adjacency matrix, however, is that it requires more memory space for storage as compared to adjacency lists. Let's focus on using adjacency matrices henceforth, assuming that memory is not a limitation in our analysis. So when we want to represent a graph as an adjacency matrix, say A, we first need to label the vertices in any arbitrary manner. Then we use the notation Aij to denote the element in matrix A that represents the edge connecting vertices I and j. So if vertex I is connected to vertex j, then Aij would be equal to 1. Otherwise, it is 0. Now that we understand the representations, we can compare their memory space complexities. In the adjacency list representation, we need an array of size V and lists totally summing up to E to show the edges. So we use theta V plus E space. For adjacency matrices, we need theta V square space as the matrices are of dimensions V by V. Now, we can better relate to why sparse graphs are better represented by adjacency lists and not adjacency matrices. Interestingly, we can also represent weighted graphs using these two representations. A weighted graph is a graph in which the edges also carry some weight. In simple words, if we have a network of friends, we can characterize the level of friendship that is very best friends, casual friends, somehow friends by weights. To do so using lists, all we need to do is to include the weight of the edge along with the vertex in the lists. But how would you do this for adjacency matrices? Very simple. Just replace the ones in the matrix by the weights of the edges. When we want to perform search over graphs, there are two algorithms that first come to mind. One of the two is the breadth first algorithm, or BFS, which is also used in many other algorithms that we will see later on in this course. The idea is very simple. Given a graph GVE and a designated source or starting vertex, say S, BFS explores all the edges starting from vertex S to find all the other vertices that are reachable from S. By reachable, I mean there exists a path from vertex S to that vertex. To state it more precisely, the BFS will give you the shortest path from S to every other vertex in the graph, given that the other vertex, say V, is reachable from S. So there may be many paths from S to V, but BFS will tell you which is the shortest in terms of the number of edges that need to be traversed from S to V. BFS works on both directed and undirected graphs. BFS works as follows. Starting from vertex S, it first searches all the vertices that are at distance k from it. So initially, k is equal to 1. Then it searches for vertices at distance k plus 1 and so forth. To keep track of which vertices have been visited and how many times it has been visited, the algorithm uses colors white, gray, and black. Initially, all vertices are white and gradually turn to gray and then black. Each node U has three attributes that BFS remembers. One is the color, which is denoted by U.color. The other is the predecessor and is denoted by U.pi. Predecessor refers to the node from which the algorithm reached the node U. So U.pi would be equal to nil when U is the starting vertex S or when the vertex U has not been discovered by the algorithm yet. The third attribute is U.d. This holds the distance from the vertex S to the vertex U, which is calculated by BFS. BFS uses a queue, denoted by Q, to manage the gray-colored vertices. Let's look at the pseudocode to understand it better. The BFS pseudocode is composed of two loops. The for loop is responsible for initialization. That is, it sets the color of all vertices to white, their distances from the vertex S to infinity, and their predecessors or parent nodes to nil. Lines 5 to 7 change the color of S to gray, makes S dot D is equal to 0, and sets the parent of S to nil. Line 8 creates an empty queue Q, which is followed by placing vertex S, which is gray, in the queue in line 9. The while loop is where all the action is. As long as there is a gray colored vertex, say U, in the queue, the algorithm visits each of its neighboring vertices, say V, and does the following checks. On line 13, it checks if the color of the newly visited node, V, is white or not. If white, it means that it is the first time V has been visited. So it changes its color to gray and increases its distance by 1 in lines 14 and 15 respectively. On line 16, it sets the parent of V to U, and finally enqueues V into the queue on line 17. After all the direct neighboring nodes of U are visited, BFS changes the color of U to black, meaning that it has searched all the neighbors of this node and found the shortest path to each of them. As an example, let's now apply BFS on this graph as shown in figure A. The first for loop in the pseudocode initializes the vertices, colors, and distances as shown here, and sets the predecessors of all the vertices to nil. Since S is the source code, we make it gray and put it in the queue. Then we dequeue the vertex with the least D value. Since the only vertex in queue is S, we dequeue it and make it black. Then we visit all the vertices that share edges with vertex S. Here, the two neighboring vertices are R and W. We change their colors to gray, add 1 to their distances, and set S to be their predecessor. So we see that with one step, we can reach vertices R and W from S. We then place R and W in the queue and repeat the process over and over until the queue becomes empty. In the end, we see that BFS finds all the shortest paths from S to every other vertex. These paths are highlighted in figure I. For instance, the shortest path from vertex S to vertex Y would be S to W, W to X, and X to Y, with a distance of D is equal to 3. In the previous example, the graph was connected. That is, we could get from one vertex to any other vertex by traversing the edges. But sometimes graphs may be partitioned such that no path exists between two vertices. In that case, the distance D would be infinity. If we denote the shortest distance between vertex S and some vertex V as delta SV, then delta SV would be equal to infinity if there exists no path from S to V. So basically, V dot D bounds delta SV from above. This leads us to an interesting property which is stated in the lemma here. Irrespective of whether the graph is directed or undirected, for any edge UV that exists in the graph, delta SV would be less than or equal to delta SU plus 1. The proof is quite straightforward. We can claim that if U is reachable from S, then V is also reachable from S, since there exists the edge UV that connects vertex U to vertex V. So the shortest path from S to V cannot be longer than the shortest path from S to U plus the edge UV. This implies that the equality in the theorem holds. If U is not reachable from S, then delta SU would be equal to infinity, and thus we have the less than sign. The BFS algorithm has another unique feature. When it is run on a graph, it creates a breadth-first tree, which is built using the predecessor attribute that is pi information stored for each vertex v. To define what a breadth-first tree is, we need to define the predecessor subgraph denoted by gpi first. So, gpi is a graph where the set of vertices denoted by vpi comprises of all vertices whose predecessors are known and the source vertex s. The set of edges epi consists of edges between vertices in the set vpi, excluding the source vertex s. With this definition in place, the predecessor graph gpi is a breadth-first tree if vpi consists of vertices reachable from vertex s and the graph gpi contains unique shortest paths from s to all vertices in the graph. Looking back at the previous example, we see that the highlighted edges actually represent the breadth-first tree. The second widely adopted graph search algorithm is depth-first search, or DFS for short. As the name suggests, DFS, unlike BFS, first searches the depth of the graph rather than the breadth. In other words, starting from some vertex S, it visits one of its direct neighboring vertices and then visits this neighbor's neighbor and so on until no unvisited vertex exists. Then it does the same for the next vertex connected to S. As in BFS, DFS also keeps record of the color and predecessor of each visited vertex. A unique feature of DFS is that it maintains two timestamps for each vertex V in the graph. The first is when V is visited or discovered for the first time. This is denoted by v.d, and at this point, the vertex V is colored gray. The second timestamp is when V's list of neighboring vertices are examined and is colored black. This is denoted by v.f. Therefore, for every vertex u, u.d would always be less than u.f, which is quite obvious. You cannot finish examining a vertex's neighbors without first visiting it. So, before the time u.d, u is white. That is, it has not been discovered yet. Between time u.d and u.f, the vertex u is gray. After u.f, the vertex u turns black, which indicates that the search on adjacent neighbors of vertex u has been completed. Like BFS, DFS also runs on both directed and undirected graphs. This is the pseudocode for DFS. The first for loop on line 1 initializes the color and predecessor of each node u in the graph to white and nil respectively. Line 4 sets the variable time to 0. The for loop on line 5 iterates over all vertices in the graph, and if the color of a vertex is white, it executes the DFS visit function. Inside the DFS visit function, it increments the timer by 1 when a new vertex is visited on line 1 and sets the starting time of that vertex to this time on line 2. Then the color of that vertex is changed to gray before entering the for loop on line 4. This for loop now checks every edge connected to vertex u to see if vertex v that is connected to u is white or not. If white, then we set the parent or predecessor of v as u and call DFS again on vertex v. Line 8 changes the color of u to black, which indicates that this vertex is done. So we need to set the finishing time of the vertex as done in lines 9 and 10 of DFS visit respectively. Now, can you guess the running time of DFS? Let's use DFS on this directed graph and see how it works. Unlike BFS, DFS does not specify any particular vertex as the source vertex. In this example, we assume that we traverse the vertices in the alphabetical order. So let's start with vertex U. Initially, U is white. Upon visiting U, we change its color to gray and set the starting time to 1. Now we enter the DFS visit function here. First, we find the adjacent vertices of U, which in this example are vertices V and X. Alphabetically, we visit vertex V, set it to gray, and set its starting time to 2. Now, we apply DFS visit on V. Its neighbor is Y. So we repeat the same for vertex Y, and then vertex X. Now, once at vertex X, we see that there are no unvisited vertices connected to X. The only vertex traversable from X is V, which has already been visited earlier because its color is gray. So the vertex X is connected to a vertex that has a timestamp lesser than itself. For now, let us mark this edge as B, which stands for back. I will explain this later on. So we leave vertex X by setting its finish time as 5 and go back recursively to vertex Y. There is no unvisited vertex from Y as well. So we increment its finishing time to be 6 and go back to vertex V. Same here. Eventually, we reach vertex U and set its finishing time to 8. Note that we change the color of all these vertices to black upon back tracing. At U, we have an edge UX which points to vertex X with a starting time greater than that of U. Let's mark this edge as F, which stands for forward. Since we search in an alphabetical order, we now start with the next undiscovered vertex, which is W. As shown in figure J, vertex W is connected to two vertices. One is Y, which is black, and the other is Z, which is white. We mark the edge WY as C for now because it takes us to vertex Y, which has a starting time lesser than that of vertex W. This leaves us with only one vertex, that is vertex Z. We set the timestamps as before, mark Z as black, and return back to vertex W. This is the entire search procedure using DFS. We see that apart from the highlighted edges, we have differentiated three other types of edges as F, B, and C using DFS. Why do we need this? These edges give us interesting information about the algorithm. For example, if running DFS on a graph does not yield any B edges, then the directed graph is acyclic. That means it has no cycle in it. In this example, since we have two B edges, the graph is cyclic. So the four types of edges that a DFS produces can be categorized as follows. An edge UV is said to be a tree edge if V is white and is visited for the first time through edge UV. The edge UV is said to be a back edge if it connects U to its ancestor vertex V. All self-loops are considered as back edges. The edge UV is a forward edge if it connects U to a descendant vertex V. Finally, a cross edge is any other edge that is not back, forward, or a tree edge. Therefore, based on the color of vertex V, exploring the edge UV gives us the following information. If V is white, then the edge UV is a tree edge. If V is gray, then the edge UV is a back edge. And if V is black, then the edge UV is either a forward or cross edge. If the timestamp of V is greater than that of U, then it is a forward edge. Otherwise, it is a cross edge. In an undirected graph, however, DFS always produces either tree or back edges. Can you tell why? Another interesting property of DFS is that the timestamps help understand the sequence in which the vertices are visited. For instance, the graph in figure A shows the result of running DFS, which when spread over the timeline as shown in figure B, helps us visualize how the vertices are searched and returned recursively. So we see here that following the tree edges takes us from S to Z, Z to Y, then X, and then again back to Z, and then to W. The other tree formed is rooted at T, which then checks V before U. This is something similar to parenthesization of a sequence of elements. In this figure, we have redrawn the two trees formed using the tree edges, and we have included the B, C, and F edges. As I mentioned before, the timestamps on each vertex can be related to parentheses. If we consider the starting time of any vertex as the left parenthesis and the finishing time as the right parenthesis, it clearly tells us the history of the vertex discoveries using DFS. This is put in the form of the following theorem known as the parenthesis theorem. Given a graph whether directed or undirected, the theorem states that exactly one of the following conditions occurs for any two vertices u and v. One possible condition is that the intervals UDUF and VDVF are disjoint, meaning that neither of the vertices is the descendant of the other. The other possibility is that the interval UDUF lies entirely within the interval VDVF. In this case, U is the descendant of V. And finally, interval VDVF lies entirely within the interval UDUF. In such a case, V is the descendant of U. Using the parenthesis property inherent in DFS, we can topologically sort the vertices in a directed acyclic graph, or DAG for short. Now, what is meant by topological sorting? It means that we can line up the vertices of a DAG such that for every edge UV that exists in the graph, the vertex U will appear before V in the ordering. Remember that such linear ordering is only possible to obtain if the graph is acyclic. Therefore, topologically sorting a DAG will result in all edges pointing from left to right, as we will see shortly. The practical implication of topological sorting are when we want to add precedence to a sequence of actions. Every morning, suppose Professor Winowitz prepares the clothing he needs to wear in the order shown in figure A. He first selects his shirt, then a matching tie, then a jacket, and so on. Running DFS on this graph and ordering the items in the descending order of their finishing times, we get the topological sort of the selections, and this tells Professor Winowitz which clothing to put on first and in what order. Note that all the edges go from left to right in the topologically sorted graph. The pseudocode for topological sort on a DAG is given here. It basically runs DFS on the input graph G to calculate the finishing time of each vertex in it. Once a vertex turns black, it inserts it to the head of a linked list. Finally, it returns the linked list once all the vertices are discovered. It is easy to see that the running time of the topological sort is theta v plus e, where the insertion into the linked list takes O1 time. Here are some exercises for you to work out. The first exercise asks you to apply DFS on the given graph and determine the timestamps and types of edges. The second exercise requires you to topologically sort the vertices by starting from vertex M. Let us now look at an application of DFS in determining strongly connected components in a directed graph. To begin, we first need to define what is meant by a strongly connected component, or SCC for short. Given a directed graph GVE, an SCC is a maximal set of vertices denoted by C, such that for any two vertices in C, say U and V, we can go from U to V and from V to U. That means U and V are reachable from each other. An example is shown in this figure. We see that there are four SCCs here. Keep in mind that no matter what vertex you start from, the final result will always be the same. So in this example, DFS was first run on vertex C, but you can start from A, H, F, or any other vertex. It does not change the final partitioning result. The algorithm we will be studying is called Kosaraju's algorithm. It finds the SCCs in a directed graph G by computing the transpose of the graph denoted by G transpose. Basically, G transpose is the same as G, except that the direction of all the edges is reversed. Interestingly, G and G transpose will have the same SCCs. That is, if U and V are reachable in G, then they will also be reachable from each other in G transpose. This figure over here shows the transpose of the graph on the previous slide. The pseudocode of Kosaraju's algorithm, which runs in linear time, is shown here. It uses two DFSs, one on the graph G and one on its transpose. It first calls DFS on the original graph and calculates the finishing time of all the vertices. Then it produces the transpose graph GT. It then runs DFS on G transpose and visits the vertices in the descending order of their finishing times as calculated on line 1. Finally, it prints the tree that corresponds to the SCCs in the graph as shown in this figure.